Welcome back. Here we are, solving trig equations, the complicated ones, the complex ones. And to do so, we will use three main strategies. This is you. You're a superhero, because you're solving complex trig equations. I apologize for the wrinkly paper once again, and my sniffles. I'm sick. But don't worry, you won't get sick. The internet will protect you. So, let's talk trig. Don't look at these yet. Look at Tom Cruise. He'll give you confidence. And ultimately, when you solve long problems, that's what it is all about in the end. Take yourself seriously. Be confident that you can get the right answer in the end. Understand the process. When you start out, you'll kind of have a good feeling for the ideas, but not perfect. You'll make mistakes along the way, but you'll kind of understand those mistakes. And then you practice. The more you practice, and you get better, and you make less mistakes, and then you start just consistently getting them right. So understand the process in the beginning when you make mistakes. Don't go, oh! Just go like, oh, I made a mistake. Learn from it and understand soon with the practice, if you put the time in, you'll just get these right flawlessly. So with trig, the big idea is that in the end, these turn into a simple trig equation. What does that mean? That means just like cos equals a ratio. And we have to solve those with the unit circle. And don't neglect those final steps, understanding the unit circle, making the mark, when to use the calculator, the plus 2 pi k, all of that stuff. I think that stuff's more conceptually, I wouldn't say difficult, but it was a bigger hurdle for us to get over, even though it's mostly review. So don't neglect that stuff. So what are our three strategies? The first one in solving complex trig is really just to get it by itself, as in a sine, cos, and tangent just isolated on one side of the equation. So here's one I took off an AICE exam. It said f of x equals sine squared minus 3 cos squared. Now it didn't say to solve it. In part 1 it said make it look like this. I said, okay. Since there's just cos squared, I'll get rid of the sine squared. Cast it out. Use the identity. Sine squared is the same as 1 minus cos squared. Multiply by 2. I combine all the like terms, and then it looks like that. 2 minus 5 cos squared. Okay. Then in part 2, the problem said let f of x plus 1 equal 0 and solve it. That pretty much means what we just figured out f of x was, 2 minus 5 cos squared, plus 1 equals 0, and we solved that. So here was kind of the starting point. And notice, there's only one trig expression in the problem, cos squared. That's why, I just get it by itself. Let's just get cos by itself, solve for it like an x. So how we do that? We combine like terms. 2 plus 1 equals 3. Minus 3 from both sides. Divide by negative 5. Negative divided by negative is a positive. And take the square root to make cos squared into cos. When you take the square root, we're not a rook. We remember that it's plus or minus, two different possibilities. So the problem splits into two simple trig equations. Certainly ones that will use the calculator, because root 3/5, that's not a ratio I recognize. So the first thing we do is draw the unit circle. Once here and once here. Since cos is the x-axis, we make the mark here for a positive value and around here for a negative value. I checked this square root 3/5 on my calculator, and it was around 0.7. That helped me estimate on the x-axis where to make the mark. Now we see our two triangles, and we can easily evaluate how reasonable our answer will be from the calculator. So when you plug in here into the inverse, you get 0.685. Now, that is radians. You say, I don't like radians. Deal with it. Start liking them. move more than like. Maybe flirt with radians and then eventually fall in love with them. Why are we using radians on this problem? Because in the beginning it showed me this. It's a domain restriction, but it's in terms of pi, so that means they only want the answer in radians. If this was like 180, we could use degrees. So they want radians. 0.685, that looks good, that looks like radians. Down here the other triangle is negative 0.685. Over here we see triangles in quadrant 2 and 3 from the negative root 3/5. And we say, how do we get this angle? Well, one is, you know, the triangle's angle right here is 0.685, subtract it from pi. You also could plug the negative square root in your calculator and it'll spit out 2.46. That looks about right because, you know, 180 is pi. That's 3.14, so 2.46 looks fine to me. Now, in the end, we don't want infinite answers here. We only want answers between 0 and pi, also known as between quadrant 1 and quadrant 2. So that's why we only take the top two triangles. We only take these two angles for our final answer. All right, let's move on to the second strategy, which is we're going to treat this thing like a quadratic. We're going to solve through factoring. So if you watched the previous video on proving trig equations, this is how we ended up in one of the problems. So this is how we solve it. 2 sine to the fourth minus cos squared equals 0. Often, the very first thing you'll do is to switch out cos squared or sine squared for the identity here. Why do that? Because when we switch out cos squared and distribute this negative 1, I notice it has the form sine to the fourth, sine squared minus 1. And that is something we can factor. This was a secret quadratic, what we called these. Even though it's to the fourth degree, you can factor it into two binomials like a normal quadratic. Rather than x and x, it would be x squared and x squared, or in this case sine squared and sine squared. Zero product property, set each binomial equal to 0 and solve. On the right side, when it's sine squared plus 1, and you minus it from both sides and take the square root, you get square root of negative 1. Nah, dog, nah. Can't do that, no real solutions. On the other side, we have sine squared equals 1/2, and when we take the square root, we get 1 over root 2. That looks familiar to me. I don't even need a calculator because 1 and root 2, that's a familiar ratio. So we draw our mark here on the y-axis for the positive, and down here for the negative. We see 4 different triangles. You could use your calculator, but you don't have to. You know, if this is SOHCAHTOA, if the opposite is 1 and the hypotenuse is root 2, it's got to be a 45-degree angle. Why are we using degrees here? Because whoosh, whoosh, in the problem, now it said 0 to 360. So you can use degrees. Thus, we get these 4 answers for these 4 triangles, and we don't have to say plus 360k because we can only have answers between 0 and 360. So if you had said, oh, right here I said a negative 45, that'd be no good. For this point right here, terminal point, you have to say all the way rotating around 315 degrees. Negative 45 does not fit between 0 and 360. So notice, on this problem, you know, we used factoring. It was kind of weird because it was to the 4th power. That was what we called a secret quadratic. And all of our methods for secret quadratics, those involving a square root, those involving fractions, those involving 4th degree stuff, they're all possible here. So if you're hazy on those, go back and take a look, because they all can happen with trig. Finally, our last strategy, turn this stuff into tangent. How we do that? Okay, we have a problem. It's got sine squared and cos squared. If this just were sine squared and cos, I would try to make this like a quadratic. I would switch the sine squared for 1 minus cos squared, and then you'd have 1 cos squared and cos, kind of like an A, B, and C for a quadratic. But it's not like that. It's sine squared and cos squared. So if you divide both sides by cos squared, sine squared over cos squared, we can turn the problem into tangent. So just to review, if it has just sine and cos in it, make it tangent. Sine squared and cos squared, make that tan squared. But if it were just sine squared and a cos, you do it like type 2. You try to make it quadratic after switching in the identity. Okay, but what's happening here, though? After you take the square root of both sides, and you get nice 3 over 2, positive and negative, we split the problem 2 ways. Notice the 2 theta, haven't changed it yet. We're not going to mess with that 2 till the very end, until we solve it going backwards. So we have our 2 trig equations. Draw the unit circle. You don't have to. It's the greatest day of your life. You don't have to draw the unit circle. I did over here for funsies because I'm a nerd, I guess. But you don't have to. You could use the fact that tangent is slope and 3/2 is kind of like a slope of 1.5. But we don't have to draw the triangle because simply saying plus pi k shows all possible triangles. So I use the inverse tan on my calculator of 3/2, and I got 9.983 radians in the negative version. Now that doesn't equal theta, it equals the inside, which is 2 theta, and now we can really see what theta is, dividing both sides by 2. When you do that, this 0.983 gets divided by 2, and the pi k gets divided by 2. Why does that matter? Because the answers it want is in between 0 and pi. So, rather than infinite answers, if we let k equal 0, you get 0.492, that works. If you let k equals 1 and add pi over 2, you get 2.06. If we were to keep going, if we were to let k equal 2 and say pi plus 0.492, that would be no good. We would be over pi, we'd be over 360 degrees. Going to the other side, the negative, if we add pi over 2, it becomes positive, and if we add pi over 2 times 2, it's 2.712. That's still under 3.14, so that counts, and here are the 4 solutions for this one. So the key thing when you start these problems is identify which of these 3 strategies you're going to use. Are you going to turn it into tangent? Are you going to solve it like a quadratic, even if it's like a secret quadratic? Or is there just one sine, cos, or tangent in the problem and you can just get it by itself? Ultimately, it's up to you to choose which one you're going to do. Later, dorks.